It's a great pleasure to be here, and thank you for your kind invite and all the hard work you and Jennifer do behind the scenes. And welcome and thank you everybody for joining the session. My name is Serdar. I'm a member of the AI Center of Excellence at Fidelity Investments and an adjunct faculty member at the Computer Science Department at Brown. My talk today will be at the intersection of recommender systems and industrial strength open source software. So we all interact with recommender systems on a daily basis, and they become central in our lives. They're widely employed in the industry. Prominent examples include online shopping sites like Amazon, music and movie services like YouTube and Netflix and Spotify, mobile app stores like Google Play and iOS App Store, online advertising, and so on. And the primary goal of these systems is to help users find relevant and engaging content. And from the user's perspective, it creates a tailored, personalized experience. And from the business perspective, it creates new opportunities. If you don't really know what goes under the hood, let me show you a glimpse of how they work. So let's take a look at classical recommendation systems. And I'm going to use an illustrative example here to see what they do. Here's an imaginary user of a movie recommendation system, Jennifer. She's a film aficionado, and like myself, she really enjoyed watching Game of Thrones, The Avengers, and Spider-Man. Next to that, here are three other cinephiles that also highly rated these three movies. So if we are to make recommendations for Jennifer, what we can do is to look at the movies that she did not watch yet and the movies that these other users that are similar to Jennifer already liked. For example, the first user likes Batman Begins and James Bond and Guardians of Galaxy. The second user here also liked James Bond and Guardian of Galaxy. And the last user also liked Guardian of Galaxy as well. So as you can see, the Guardians of Galaxy is our top contender here. And it should be the first movie that we shall recommend to Jennifer. And notice none of these users like The Walking Dead, so we probably should not show it to her. So in a nutshell, this is how classical recommendation systems work, by finding similarities between movies and users and connecting the two together. These are also referred to as collaborative approaches, since they build on item-to-item and user-to-user collaboration. Okay? And a natural next question that people asked, given, this is all not nice and fine, but, we didn't use any information other than the movie ratings. So the question is, just looking at the ratings and user similarity provides us enough data to build performant recommender systems? And the answer to that question is no. And if you think about it, we know a lot about Jennifer. We have a lot of information, and that's called the user context. And analogously, we know a lot about these movies as well, which is known as the content features. So when we go beyond the classical recommender systems that works on collaborative filtering approaches, we have more advanced algorithms that are content and context aware. So the challenge is, how can these systems understand and make sense of enriched content and context information? And that's exactly the topic of my talk today. My goal is to provide you with details on content and context-aware recommendation systems. And the main components of this will be the user context, the content features, and their historical interaction. While doing that, I'm going to cover a number of important areas from artificial intelligence and machine learning. And this talk will be a practical talk. I'll present several use examples from open source libraries. I'm most familiar with the libraries that we developed at Fidelity, but I just want to mention that what is important is not necessarily one particular implementation, but the main ideas behind them. So any other alternative should also work fine. Okay, so here is what our roadmap today looks like. We will start by building on context for our user representations. Here we will study pattern mining and the sequence to pattern generation library in particular. Then we are going to look at the other side of the coin and how to build content features. This is the movies in our case. And here we are going to turn to natural language processing, NLP, and the TextVisor library. Once we have the user data and the content data in place, we might want to do a bit of cleanup and remove redundant attributes. For that, we're going to turn to feature selection and the selective library. And in step number 4, once we have this nice data in place, we will combine that with historical engagement between movies and the users and build a recommendation algorithm based on a particular approach from reinforcement learning that is known as multi-unbanded algorithms. Finally, we will look at how we can evaluate such systems in terms of both recommendation metrics and fairness and bias considerations. So one thing to mention is, my goal is not to come up with the best recommendation system. Clearly, that depends on the application and particular data sets, but our primary focus will be on the fundamental concepts here. So in that sense, I'm only using recommender systems as a case study, and these algorithms and libraries are useful beyond recommendation applications. So in fact, each one of them is self-contained on its own. So what that means is you can pick out one that you like and use it in other domains. I'm just using recommenders to make the ideas more concrete here. What this also means is if one of the tools is not interesting for you, or if I lose you during the talk, you can come back in the next one, since these are independent from each other. So overall, this talk will be successful if you have built some familiarity with these concepts, quickly evaluate whether these libraries can be beneficial for your cases, and have a pointer in your mind with practical use examples on where to start. So with that, if there are no questions and comments, let's dive in. And before I proceed, a big thank you to my collaborators. There's lots of focus on open source software in this talk, but these areas are lots of open research directions as well. And here's a list of publications from our group as a reference that talks in technical detail about these algorithms and open research problems. Big thank you to my collaborators. All the credit goes to them, as well as our leadership team at Fidelity and the open source team who is supporting these initiatives and helping us to share both our research and our libraries with the community here. Okay, step number 1, user context representation. Let's start with sequential pattern mining. In our movie example, we would like to have a user context representation for Jennifer. And in order to do that, what we can do is to search for interesting digital behavior and digital patterns. And then we can check whether Jennifer exhibits that pattern or that behavior, which can generate us a vector representation for the user context of Jennifer. The question is how to find such interesting patterns and how do we even define what is interesting. And for that, we're going to turn to sequential pattern mining and look at the Seq2Pat library. So the best way to introduce the problem is to use an example. Consider an online bookstore. I have digital behavior of a number of users here captured as a sequence of web pages or ads that they might be visiting or they might be seeing. Some of these sequences leads to positive outcomes, which could be maybe purchasing a book, and others might not. In this example, I have 6 users and 6 digital sequences. And the first sequence leads to a transaction, and the last sequence leads to a transaction, and the others don't. So this is a toy example, but you can imagine like I have millions of users and hundreds and thousands of such sequences in my databases. Okay. So given this data set, the main goal behind sequential pattern mining is knowledge extraction. So for example, let's take all the positive transactions and look at what is common to them. For instance, what we can find is that the users who are logged in and checking out traditional printed books, who spend at least 10 minutes and a certain number of pages, for those users, the probability that they're going to make a purchase jumps to more than 90%. Okay, this is the type of knowledge extractions that we would like to achieve by looking at the patterns in the sequence databases. And we could do the same on the analogous side, on the counterpart, for users who are unhappy or for users who did not lead to a transaction and find what is common to them as well. And then what we can do is to check whether Jennifer exhibits those behavior and use those type of features in our context representation for Jennifer and utilize this information as part of our recommendation system. Here is an illustrative example. I have 4 sequences here. The first one is A, followed by C, followed by B, and followed by C, and so on. It might be even, it's a difficult, simple example, it might be difficult to find the frequent patterns. So I'm going to reveal it. Here, ABC is a frequent pattern. Notice that there might be gaps between these patterns. So the algorithm should be able to understand that there are some superfluous entries in between. And here it occurs in 4 of the rows. So this is the most common pattern, in fact. Another common pattern is the CB with frequency 3 that occurs on 3 rows, that is exhibited on 3 users. And in general, the objective of sequential pattern mining is, given this type of interaction data, such as maybe digital behavior, to find patterns that occur in a minimum number of sequences. So there's some threshold that we want to beat, and we want to find the ones that are frequent. So wouldn't it be nice to have some software to automatically extract such patterns from sequence databases? And this is where the sequence-to-pattern library comes into picture. In fact, it does something also called constraint-based sequential pattern mining, and I'll mention what that is in a second. So this is a library that we built in collaboration with the Carnegie Mellon University, and let me walk you through what it does on a real example here. So this is exact code. If you write this, this should work. I have a sequence database, very similar to what we looked at together. So I have 3 sequences. The first one is AA, BB, AD, and so on. Given such a sequence database, I can create a sequence to pattern object. And what I can do on that object is to ask for frequent patterns that occurs, let's say, at least 2 times, meaning at least on 2 rows. So that's the goal of this library. And it finds me the patterns with some minimum frequency. And what I can also do is to incorporate additional information. For instance, maybe I know the price information of the books on those visits. So in these events, I can have additional side information, for instance, the price, or maybe the timestamp that people spend on these websites. And I can use those attributes to focus my search only on patterns that have desired properties. So here I'm asking for patterns that happens at least twice in the database, but at the same time, that's not enough, but I also ask that the pattern to have an average price between a certain lower and upper bound. And I can add other arithmetic constraints as well, just to focus my search on really interesting patterns that I can define what those properties are. So this is a library written in Cython with an efficient C++ backend and a high-level Python API. And we typically employ pattern mining on millions of events, and that works within a few minutes and so on. We presented this work at Informs and AAAI in the recent years. So that is the first step of our approach. Any questions, comments so far?
Serdar, let's see. I see a couple of questions that have been put over in the. I'm actually looking at chat right now. Mm-hmm. Let's see. Mark Hutchinson, I think, asked, "Is there a difference between user and customer?"
No, I was using them interchangeably. So.
Oh, okay. Okay. Yeah.
Clients, users, customers, and
yeah.
users.
Arun Jain, actually going back to, let's see, just a little ways. If you could highlight examples of each of these libraries, or let's see, of where each of these libraries can be used as you talk through them, that would be great. So I think that was more of a comment.
Yes, and I hope this example helps to that purpose.
That's all I got. Yeah.
All right, perfect. Thank you very much for the help. And moving on, let's. In the previous section, we looked at the user context, and now let's turn our attention to content featurization. So, and switch gears to natural language processing. In this section, we will look at text featurization provided by the TextVisor library. So how to make sense of language and text has been a challenging question for AI, and recent major breakthroughs in machine learning came from the applications of deep learning and deep learning architectures to natural language processing. So we as humans understand language and text, but machines don't. So we have to featurize unstructured data and turn them into numeric vectors so that the machines can operate on them. And this process is typically known as creating an embedding. The high-level idea is somewhat straightforward. You take a word and you map it to a numeric vector in the space. Here's a famous example that you might have seen before. If you look at the relationship between the numeric representation of the king and the queen, that relationship is very similar to the relationship between man and woman. In fact, if you do a bit of arithmetic and subtract man, the vector that corresponds to man from the king, and add it to the vector that corresponds to woman, believe it or not, the vector you get as a result is the vector that corresponds to queen. So no person went in there to write that logic, but the machines were able to automatically infer that on their own. So that is very cool. And today the NLP research has reached to a state where machines can reason about the semantics behind the language just like we do. And this is what's behind Siri on our mobile phones and Alexa, and that's how they understand it. In fact, the relationship applies to arbitrary objects as well. So I have the countries and capitals here. So if you know the relationship between Spain and Madrid, you can probably find the capital of Turkey as well. The most common incorrect answer is Istanbul, and the capital is Ankara, in fact. Now, recent developments in the community provided us with practitioners with a lot of rich set of tools. Popular examples include NLTK, GenSim, Spacey, and more recently, Allen NLP, Flare, and Hugging Face transformers. Most of these libraries come with pre-trained models. So what that means is you can immediately take these language models and use them in your applications. But still, the availability of various techniques in standalone libraries doesn't provide immediate solutions. So you still need to work out with different tools and build a custom layer on top to experiment with the best approach for your use case. These libraries have different input and output specs. Some work with NumPy arrays, some work with sparse matrices, some with PyTorch tensors, list of floats, and you name it. And when your scenario and use case changes, you have to redo this from scratch. That's a cost that every practitioner has to pay. And NLP is a very fast-moving field, so new techniques and methods are introduced on a rapid basis, so you have to keep up with it all the time. So to combat this challenge, we have come up with a unification that represents the text featurization methods. And to do that, we use context-free grammars. So in essence, we are using NLP to rule on top of NLP. And the main idea behind TextVisor can be captured by this formula that says TextVisor equals to an embedding plus 0 or more transformations. The grammar is on the left, but I'm not going into the details of it. So what is the missing NLP technique library on the right of the slide? Is it this slide or the previous one? Oh, it is the next one to arrive, if that was the question for the purple, because this is a fast-moving field. There are many tools that are being introduced basically on a weekly basis. So I'm not going to go into the details of how this grammar works, but essentially it allows us to build and design embeddings from well-defined components. So one of the components could be the word embedding, as we have seen in the king and the queen example, and some transformation, which kind of stands for getting these word vectors and then doing a dimensionality reduction on them. So you might go to a smaller, more robust representation. So the TextVisor library provides us with lots and lots of different rich set of embeddings. So I showed the word to vec, but also there are others, to name a few: TF-IDF, document to vec, BERT, Flare, OpenAI GP2, and many others. And on top of that, you could do transformations for dimensionality reduction, such as latent Dirichlet allocation, non-negative matrix factorization, pooling operators, as well as singular value decomposition and manifold approximation. If you don't know what these mean, it's okay. Think of it as getting some word representations and lowering their dimensionality so that they are more compact, they are more robust. So how does that look in practice? So here's the TextVisor library that we presented our context-free grammar behind it at the AAAI this year. I have a set of documents here. So let's say I have a document, maybe another document that's a little longer. What I can do is to initiate an embedding. So in this case, I'm using a counting frequency-based approach, which is called TF-IDF. So one of the embedding parameters here. And if I take my embedding and fit transform my documents, what I will get is the output is the vector representation. So that these are the king and the queen and the vectors that you've seen in that picture. I can change what my embedding is. So maybe I can use TF-IDF, but do a dimensionality reduction. Let's say non-negative matrix factorization. In fact, I can chain these transformations, maybe do a decomposition on top of the matrix factorization. Or maybe I can use the word-to-vec example that we have seen, or maybe another word embedding, but this time I'm going to use the BERT language model. So by changing what the embedding structure is, I can get different vector representations so that I can have rapid experimentation and see what works best in my use case. One thing to mention is the resulting vectors are fine-tunable, meaning if you take these vectors and build machine learning models and you optimize those models for downstream tasks, these vectors will continue to optimize themselves as well. The grammar also allows us to build arbitrarily complex embeddings, but I'm going to skip that, and you can find examples in the GitHub repository. Okay, so far in the previous two sections, we looked at the user context and the content features. So we're slowly building our context representation. If you bring these two together, this consists quite a bit of information. And as an optional exercise, what we can do is to conduct what is known as feature selection. The idea being we might want to remove some redundant or features that don't carry much signal. So we can eliminate them. And to do that, we turn to feature selection and the selective library. So this is what it looks like, what we have so far on our context representation. We have some input from the digital behavior of the users. I have the NLP text embeddings of the content. And I also have some historical data that tells me whether this user with this movie, whether they watched it or they liked it. So some form of label that represents their interaction data. Now notice that there's a trade-off here. The more number of features, so the more columns I have in this matrix, the more rows, the more observations I would need to effectively train that system. So feature selection helps us to keep that size manageable, as well as the more number of columns, features, the longer the runtime will be. There are many feature selection techniques, but essentially they fall into these four categories. So what I can do is either supervised or unsupervised fashion. And by supervised, I mean using the rewards, the 0-1 labels that we have for the interaction on that. So the simplest approaches would be the variance. Good question. If you have more columns, would you need more reward columns? So no, because the reward corresponds to the interaction between a particular user and a particular content. So if I represent the user with 10 columns or 20 columns, doesn't really matter. The interaction I'm looking at, this user watched a particular movie. So that the reward corresponds to that binary relationship. The size of my dimensions depends on how many features I include in my context representation. So I hope that clarifies the question on the chat. And in terms of feature selection, what I can do is I can look at individual columns, and I can look at, if they don't have much variance, they're basically static columns, so I can drop them. So variance thresholding is the easiest, simplest thing one could do. A step beyond that is I can take two columns and look at their pairwise relationship with some different correlation techniques, and then say that if these two are very correlated, then I don't need to include probably both of them at the same time. So I can drop one of them. And the techniques at the bottom are supervised. See, they are using the interaction data, whether the user watched the movie or liked the song, etc. And what I can do is I can take one of the columns and see how it statistically connects with the labels that I have. So I can see the dependency between these two random variables. And if they're independent from each other, then having this feature is not very interesting, so I can drop it. Or I can even build a function, a model from this feature to the labels that I observed in a linear fashion, for instance. And then I can look at my coefficients of my regression, or in a nonlinear fashion as in tree-based methods, and look at my feature importance and drop features that are not very important. So there are other techniques as well, but I just wanted to give you a flavor. And how does that look in practice? So here is the selective library. I have a data set. This is a toy data set with some data and labels. So the data here corresponds to the matrix that I showed, and the label is the rewards column we just looked at. What I can do is to create different selection methods. So I can have the variance or the correlation or the statistical or the model-based linear or nonlinear models. And then fit transform on my data set in order to arrive at a subset of the data. So if my variance threshold is 0, it's going to drop any columns with a 0 variance. Or if my number of features is 3, it's going to pick up the topmost 3 features that is most important according to my linear regression. And there's more than 25 plus supervised and unsupervised techniques built in this library that you can use. And it's white box in the sense that you can play with each one of them and look at what's their feature importance and how are they interacting internally. And this concludes our data setup. So we have done all this work up until now to actually build a recommendation algorithm. And this is where the multi-unbanded framework will come in. We created our user representation, we created our content representation, we cleaned it nicely, we combined it with interaction data, labels and rewards, and what remains is to build a machine learning model. And for that purpose, we are going to use the MABWiser library. So let me review very quickly a few concepts about multi-unbandeds. What is multi-unbanded? So quick example, in daily life, we frequently face situations in which we must choose between a known familiar entity and an unknown one. Okay, for example, you go to a restaurant, you look at the menu, do you go with your favorite dish or do you try out the daily special? So the choice between different arms, different options, that depends on your past experience. So that's the learning bit, as well as the particular situation, the context, your mood of the day that you are currently in. Upon making a decision, you see the reward of that decision, and that feedback loop takes that reward back into the system to revise your expectations to make next decisions. So in literature, these problems are called online sequential discrete decision-making problems, for which multi-unbanded algorithms are pretty good solutions that offer effective solutions. Notice one thing, at each turn, we face a dilemma. Do we choose an arm? Do we choose an option with the highest expected reward? Or do we choose an arm that we don't have much information about, but potentially learn something new? So that's the exploitation versus exploration trade-off. And in general, reinforcement learning algorithms have to balance that trade-off in order to maximize the long-term cumulative gains as you play this game over and over again. And the banded algorithms are applied in the industry and in the literature in numerous domains. I listed a few here. My favorite example, the movie artwork personalization from Netflix. What they essentially do is to use bandits to select the poster image to display when they are recommending a movie to a user. So for the same movie, different people might see a different poster representation. And they use a multi-unbanded approach for that. While these algorithms are really nice, there were not many options to use map algorithms in the Python tech stack. And to fill this gap, we built the MABWiser library that we presented in a number of publications. And here is a concrete usage example. I have 2 arms, essentially 2 movies to recommend, and I have some historical data, some decisions I made in the past. So maybe I decided to show movie 1, movie 1, movie 2, movie 1 under different context representations that we built using sequential pattern mining for Jennifer, or to be built using content featurization, using the text info of the movies, etc. And as a result, I received some reward information. Maybe that's the number of minutes that the user watched the movie, or it could be binary, as we have seen in the previous example. What the map algorithms do is I initiated an object with the options I have. So I have 2 arms here, and I trained my bandit using a learning policy. So there are different options to select here and different combinations of different policies based on the decisions, rewards, and the context I have seen. So once I have a trained expectation model, what I can do is for the next user, I create the next test context for that case. And what I can do is make a prediction on what should be the best recommendation for this new context. And that becomes my recommendation output. Now, notice the online learning nature of this algorithm. So this recommendation could become my next decision. I can record the reward that corresponds to this decision, and I can record the context under which I made that decision, and I can update my expectation and ask for the next decision again. So these algorithms are naturally good applications for continuous learning, as in recommender systems, to keep up with customers' engagement and the users' interests. There are many more examples on the GitHub repository if you want to check it out. And finally, what remains to be seen is how these algorithms perform in practice, both from a recommendation metrics perspective, as well as fairness evaluation and bias mitigation. And for that purpose, we're going to look at the Jurity library. I'll jump right into the usage example here. So in my historical data, imagine I have some actual interactions, whether people clicked on the movies that I recommended or not. And I have some predictions that comes from my model. And my model could be a multi-unbanded model or any other model in general. So I have the actuals and I have the predictions. What I can do is I can create different metrics. So here are the metrics that are typically used in the recommendation field, such as the click-through rate is like a very standard metric. But also there are others like NCDG, which also accounts for not getting only the click, but also at which position you're getting a click if you're making top K recommendations, as well as some others like precision recall and mean average precision. You can generate those metrics and then get their scores given the actuals and the predictions from your model. There is a fantastic question from Amin. How do you approach this when you don't have any user interaction for completely new products? And I'll come to that in a second, Amin. Let me conclude here quickly. And notice, these recommendations could come from other algorithms aside from multi-unbanded as well. So these libraries, as I said, are independent from each other. And next, if we know some membership information on protected attributes about our population, for instance, it could be race, it could be age, it could be gender, etc. But I have some membership information, whether the individuals belong to some protected groups. Given such information, what I can do is I can look at different famous metrics. There's a number of them in the literature. Here, I'm using one that's called statistical parity. What it basically does, it looks at the people in one class and it checks whether it has the same likelihood to receive a positive prediction compared to the other people in the other class. And then it can tell you whether this falls into reasonable bounds. And you can ask your metric based on your membership status as well as your model's predictions to see if the fairness metrics look reasonable for your application. And if you have some unwanted bias discovered in your algorithms, what you can also do is bias mitigation. So in this case, I have a bias mitigation technique here called equalized odds. And what it does is, given the predictions of my model and the protected attribute, the membership information, it tries to change the predictions of the model. It's like a post-processing kind of technique. It tries to change the likelihoods and the predictions of the model in such a way that the changes are minimal, but at the same time, the odds for these privileged and underprivileged groups to have some equal representations. And you can use these fair predictions and fair likelihoods in the remainder of your application. So to summarize, overall, if I bring all these components together, we can build some entire machinery for recommender systems. At the heart of it is the multi-unbanded algorithms that knows how to deal with the exploration dilemma, as well as keeping track of reward in an online fashion and taking into account the feedback that it receives from the users. It is based on the user profiles for which we can do pattern mining, as well as content features that we can use the text featurization with feature selection, as well as the evaluations that we can do to understand the performance of our system. And these libraries and techniques could be useful in general. They are general algorithms from pattern mining, natural language processing, and feature selection. And I hope these could become helpful in your own applications as well. And that concludes my talk. I'd like to thank you very much for your attention and happy to hear your comments and questions.
Serdar, thank you very much. Great job. What wonderful job. Really good presentation. Let's see. So Asmin posted a question in the Q&A, and I think, have you already answered that question? Or I know.
have not answered that question, and I'm going to answer that right
Okay.
now. That's a fantastic question. So to repeat for the audience, Amin asks, what do I do? Let's say if I have a new product and if I have a new application for which I have absolutely no interaction data, what do I do then? And that is a very practical problem. It does occur in practice. And I'd like to go back to this slide. In fact, I'd like to point out this second paper here, active learning and item selection. So we have some algorithms. What you can do is, you can try to understand. I mean, one thing you could do is you don't assume any prior, and you could start with a randomized recommendation and try to build that interaction data. So that's one approach. That's the simplest thing you could do. The other is you can try to do that in an active fashion, in the sense that what would be the best reward or the learning that you can have to get feedback from your users that would enable you to quickly move to this interaction data. So that's an optimization problem in and of itself, and you can solve that problem prior to running your recommendation algorithm and use those items, those movies for your recommendation in the initial warm-up phase. And that problem typically referred to as the cold start problem in the recommendation space. You can do data augmentation. You can bring in additional data, and you can do some cross-domain recommenders. So maybe for the movies, you might know about the books that you might want to leverage some information, as well as other transfer learning. So some learning from another domain adapted to your application here are typical approaches. So I tried to provide some general idea, but that's a very good question. Cold start literature is quite rich in terms of how to deal with that challenge.
Okay, so let's see. I'm looking at Q&A, and I'm actually scanning chat as well. I'm looking to see if there are any other questions other than just kind words, right? Thank you for the talk. Excellent presentation. Let's see. I think Mark Hutchinson earlier at about 12:30. Serdar, I just want to make sure what is the missing NLP techniques library on the right side of the slide? I think you answered it as you were going through. That was the reference slide. And then if you have more columns, would you need more reward columns? Anyway, that might be too far back, or you may have already answered that one. I'm trying to kind of sort through just to make sure that we've addressed everything.
And don't forget, everybody, I posted again at the up in the chat just a little bit that we're doing some giveaways. And so we would love to have you register for those. And then there's also information about the next meetup, registration about all things open, and of course things that we're doing to stay safe. So I did repeat the same information twice in the chat just in case you missed it up above, but feel free to click on any of those links and let us know if you have any questions.
And Serdar, Mark did let me know that you have answered all of those questions. So my apologies for being repetitive there.
Yeah, no problem. I saw one question from Arun for other libraries, and that's a good pointer as well. As I said, any alternatives would also work fine. What matters is the algorithms here. And to name a few, on the recommendation side, I think the easiest places to start would be maybe the Google's TensorFlow recommenders, as well as Microsoft recommenders that has a suite for recommendation algorithms. On the text featurization side, I had the slide that mentions a number of open source software for the NLP space. That's where there's a lot of tools in that domain. And for the recommendation evaluations, the options are a bit more limited. Some of these reco libraries have built-in metrics that are in there, but the Jurity library that I showed is standalone, so it could be used independent of the reco systems. And for bias and fairness mitigation, IBM 360 is a very nice tool, as well as Google has a interactive what-if analysis tool that is not programmatic, but that's interactively used from an end user point of view. That's another alternative. So I hope that gives some pointers on other libraries that are widely used.
Sir, I think Gail Brown had a question over in Q&A. What's the language used for these algorithms?
Perfect question. All of these libraries are written in Python. So these are all the code I have showed, all were in Python. The sequence to pattern generation library has a C+ backend, so it's actually written in Cython for efficiency purposes, but from a usage perspective, you only interact with a Pythonic implementation. So it should be very high level, as I showed on the examples.
Perfect. I think Mark, had one more question. Could you use the hypothesis library to generate data? I think he just posed that in chat. Sorry.
Yeah, I've seen that. Thank you for pointing, Mark. I am not familiar with the hypothesis library, but if I assume that it creates some mock data, yes, of course you could do that. But does that data set is it a representative data set for the application you want to use? That's the main question there. If that's not the case, the recommendations you will get will not be able to generalize to your application.
Roberto Cuba said, for text featurization, do libraries usually provide an easy way to further train or specialize their pre-trained models?
That is correct. And I briefly mentioned that in the TextWiser slide, where the vectors that we are getting once we feed in the unstructured text data, they are, when available, are also fine-tunable. And that's a very important property, so that once you take these vectors and use it in downstream models, maybe as part of your multi-unbanded or any other machine learning model, those vectors can also be updated. So that's known as fine-tuning. And that's a very important property for adapting pre-trained models to your domain. And you have that option if you use the TextWiser library for the models that support it.